get ready for the streaming. So. Okay. Okay, so welcome everybody to the virtual seminars on complexity. This is the third appointment. I thank all the speakers to be here this afternoon and also all of you, the participants. We have already scheduled a series of seminars till December. But if you want to give a seminar, if you have some proposal for 2021, we'll go on with that. Again, the schedule will be every 2 weeks. We'll have 2 seminars. That's more or less the idea. And if you go to our webpage that you can find probably in the email I sent you, you can see the next seminar for October. So we started in September, and we had 2 seminars on COVID-19 from 2 different perspectives. One from Andrea Crisanti and the other from Yamir Moreno. So, and you can find them on YouTube. And then 2 weeks ago, we had Francisco Rodriguez from São Paulo and Asaf Zariski from Ben Gurion University. The topics were different. One was epidemic networks, and the second was on deep learning for melanoma. Again, if you missed the seminar and you'd like to hear about them, please go to our YouTube channel. And you will also find these 2 seminars of today recorded on YouTube, thanks to the speaker who have agreed to be recorded. The next seminars will be 20th of October, and we'll have Michael Small from the University of Western Australia and Filippa Valdera from the University of Milan. So, a few technical information before we start. Each seminar will be about 40-45 minutes, and there will be a discussion at the end of each seminar. Since topics are different, when the topics is very related, then we do all the discussion at the end. Today topics are a bit different, so we'll do at the end of each seminar. So please post your questions on the chat, and I will read them to the speakers. And then even you can post even during the seminar. So today we have 2 different topics, as we said. The first seminar will be held by Stefan Thurner. Just a few words about Stefan Thurner. He's full professor for Science of Complex Systems at the Medical University of Vienna, where he chairs the section for Science of Complex Systems. He's also external professor at Santa Fe Institute and senior researcher at IASA, and president of the Complex Science Hub in Vienna, the interdisciplinary center. His work has been covered extensively by media of all sorts, I mean, from BBC to Nature and so on, and featured in many journals. So, and was also elected as Austrian Scientist of the Year in 2018. So there's many contributions of different aspects of complexity theory. So we welcome here Stefan Thurner, and please, the floor is yours.
Thank you, Stefano. Thanks for having me in your seminar series. Very nice initiative. My topic is about complex systems and the statistics that we find in complex systems. So complex systems are what? Typically, we have many components in a complex system, and these components are linked to each other, very often through kind of networks that tell you which component is linked to which other and interacts how, in what way, and at what times. And in essence, this means that the components of a system, of a complex systems, they influence each other. And as a consequence, they are tightly correlated. And very often the system is small in the sense that the underlying networks have a small diameter that within a couple of jumps you can reach the whole network. And there's simply no way of expecting, if you look at the complex system, that you should expect it to have and to show Gaussian statistics. Gaussian statistics is the kind of statistics that we all should know. And this is this extremely beautiful thing that appears in so many uncorrelated systems, or systems where you have independent sources of error. So I think most of you will know or will have heard the term central limit theorem, which is at the very heart of the Gaussian statistics, and basically tells you that if you add random numbers, which are not too crazy, or that are all from a distribution that has at least variance, then one should expect that the sum of random numbers follows a Gaussian distribution. And since almost every measurement process includes additions of different sources of error, most measurements, or many measurements of non-complex systems, show indeed Gaussian statistics. But as I said, in complex systems, that's not the case. And let me show you a few examples. So all of the work that I'm going to show you is published. So here you can find most of it. So the talk is centered around two motivations. The first motivation is that in complex systems, we see power laws everywhere. It's almost as if they were pests. It's relatively hard to control these power laws, not really computationally, but compared to the Gaussian statistics, it's very cumbersome to deal with power laws mathematically. Let me show you a couple of examples. So power laws we see whenever we have a log-log plot and we see a more or less linear distribution, a straight distribution, at least in the tail, and then we see that it's more or less a power law. So if you look at the populations, the distribution of populations in cities, you see that the tail of this distribution is a power law. There's to the left of the distribution, it's certainly not a power law. You see a shoulder, a round shoulder. It's not a power law, but what is interesting in most distribution functions is not the left-hand side, but the right-hand side, the large outliers that are very often responsible for the big catastrophes, for the big effects, for the big for the truly interesting behavior of a system. If you look at rainfall, how much rain does fall in a certain area, that's a power law. Again, it's a shoulder, but certainly over many orders of magnitude, you have a power law decay of rainfall. If you look at landslides, if mountains come down, how much dirt is coming down? If you look at many different landslides and do a histogram, again, you see power laws. If you look at damages that occur due to hurricanes, power law. If you look at the credit size between financial institutions, it's very nice power law. If you look at forest fires, the size of forest fires in different locations, anywhere in the world, it looks very much like a power law. If you look at moon crater diameters, it's a power law. So that's the sizes of moon craters. Very beautiful power law. Here you don't see any shoulder. Keep that in mind. We might discuss this toward the end of the lecture. If you look at the energy distribution or the peak intensity of energies from gamma rays from solar wind, almost a power law. If you look at movie sales, if you look at healthcare costs, or in particle physics cross sections, you see a power law tail. Again, a shoulder, but the tail, the right-hand side of the distribution, follows a power law. If you look into books and if you start counting words in your books and do a frequency a word frequency distribution. So you ask yourself, what's the most frequent word in a book? And you plot it on the first entry in your histogram. Then you will find that the second most frequent word appears more or less half as often as the most frequent word. And the third most frequent is a third of the most frequent word. And the 100th most frequent word is about 1 divided by 100, 100th of the most frequent word. So that's a very famous power law. It's called Zipf's law. It's a power law with an exponent of -1. If you look at citations of scientific articles, the histogram of citations, you see a shoulder, and to the right-hand side of the distribution, certainly something that looks like a power law. If you look at website hits, book sales, telephone calls, earthquake magnitude, again, you all know that's the Richter law. That's the size of the earthquakes. So the x-axis here is a logarithmic number, as you all know. Seismic events, the number of events also follows a power law. If you look at social phenomena like wars, war intensity is a power law, killings in wars is a power law, sizes of wars a power law. If you look at how wealth is distributed in the US and also in other countries, if you look at the wealth distribution of rich people, it's a power law. Family names in the US are distributed as a power law. And. Here's a list of the ands. We haven't talked about networks at all. We haven't even touched the allometric scaling laws in biology, of which there's maybe hundreds. We haven't talked about dynamics in cities, fragmentation process, random walks, blah, blah, blah. So it's almost as if the Gaussian distribution does not exist. It's really, really hard to find Gaussian statistics in complex systems. And as you have seen, it's not all exact power laws, it's deviations from power laws, but it's not Gaussians. That's what's important here. One has to be a little bit tolerant. It's not Gaussians, it's not exponential decays in these distribution functions that I've shown you. It is maybe not exact power laws, can be something like log normal distributions or something very similar to power laws. Where do power laws come from? So there's not infinite ways of possibilities. I list 4 of maybe the main routes towards power laws. Criticality is one route. Criticality is something that physicists know. That's the physics. That's what's happening in the physics or at phase transitions. So when a magnet becomes demagnetized at the critical temperature, you see power laws emerging that come from the fact that correlation lengths are diverging at this point. So at a very special point, you see power laws emerging at phase transition phenomena. Power laws emerge at self-organized criticality. That's a little bit of an extension of criticality, where you don't need to fine-tune towards critical parameters. You don't have to find a transition temperatures or critical pressure or something like this. The system looks as if it automatically finds a critical point. A simple example is sand pile models, where sand piles are organizing towards a critical slope, in a self-organized way, and the power laws there is the avalanche size of slope, avalanche sizes of sand that is going on, that is going off in avalanches if you are dropping sand on a pile. Then there's multiplicative processes. Multiplicative processes themselves give you log normal distributions. However, if you impose certain constraints on these processes, then you can get exact power loss as a whole. There's a huge number of processes that show power loss that come from these multiplicative processes. And many of you will know that that all sorts of preferential processes can lead to power loss. Network growth of the Barabashi-Albert model is one of these examples. So these are very different types of processes here. Is there an underlying root? Is there something like the central limit theorem behind all of these processes that explain the origin of power loss? That's motivation 1. What's motivation 2? Motivation 2 is the following. Most complex systems are not in equilibrium. They're driven. We all know what a driven system is. If we stop driving it, it relaxes to a ground state or to a metastable state. Yeah, for example, your computer, if you take it off the power, it will relax into a sleepy state. And if you don't turn on the power, it will no longer be a complex system. It will be a dead thing. So if you think of a driven system, you can decompose the dynamics into a driving process. So you're putting energy into a system, for example, and there's a relaxing process. That's the process that, if you should turn off the driving, brings the system to a ground state or an intermediary ground state. Okay, I think that's a pretty general statement, and cannot be terribly wrong if you state that. It would be nice to have a statistical theory for driven non-equilibrium systems. This wish has been around for, I don't know, certainly more than 100 years. And if we at the same time could explain the abundance of power laws in complex systems, that would be, of course, fantastic. That's the second motivation. Let me mention that many complex systems are also path dependent. What does path dependent mean? That future events, future states of the system, they depend on the history of the past events. So the future depends on how the system got to its present state. Yeah, many systems, especially those that have a memory of some kind, are of course path dependent. It depends on your education, what your next possibilities in life are, for example. Okay. Many systems are of the kind that, as they progress, the possibilities for future moves or future states get smaller and smaller. We call this type of process sample space reducing processes. So SSR, I'll say SSR in the future, so sample space reducing process. And what is that? If you imagine that you have a set of dice in front of you, so the first die has one side, one face. So every time you throw it, it gives 1. That's a stupid die. But then you have die number 2 that has 2 faces. That's a coin. You have a 3-faced die. Hard to draw it. But you have 3 states that you can throw. Then you have a 4-faced die, etc. Up to a die that has n faces. Okay. Now a sample space reducing process is that you take the largest die that you have, you throw it, and whatever number it gives, let's say this number is 13, then you take die number 13, the one with 13 faces. You throw this one again, and you get the number between 1 and 13, and let's say you get 9. Then you take die number 9, you throw this one, and you get 7. So the number always must get smaller. With every throw of the die dies, you have to take a smaller die until you reach the coin, and then your process is over. You've reached the smallest thing. Then you have to restart the process. So that's an example of a sample space reducing process. I'll give you more examples, but here's a little bit for notation. So if omega is the size of your phase space, is the number of possibilities that you have, then just look to the right. Your phase space volume of the die with n phases would be n. There's n possibilities that you get when you throw an n phase die. And if you take the process seriously that I just told you, then the smaller dice are just a subset of the outcomes of the smaller dice is just a subset of the bigger dice until you reach dice number 1, which always gives you only one result. So when you reach the lowest state, then you have to restart the process, and you have to go up, put in energy, and increase your number of possibilities again. Now, I might have lost you. Let me show you another example for a sample space reducing process. Language, for example. You start out with n possible words. It's the English dictionary. On the left side, you see all possible words in the English dictionary, and you randomly pick. Now you want to produce a sentence. You randomly pick one word. Let's say that word is wolf. As soon as you pick that word, you reduce the possibility of other words that could follow it. So grammar imposes a limit to, or imposes a small subset, or no, it's still a big subset. It imposes a subset of words that you can use as a verb. And as soon as you pick one of the possible words, maybe howl or something, then English grammar forces you to use an object, and object can only be a noun or something, and that reduces further your sample space or your set of possibilities. So as you produce a sentence, the longer the sentence gets, typically you're reducing the possibilities for the next word as you go along. That's a sample space reducing process. Let me show you yet another sample space reducing process. Look at the right-hand side. There you see the staircase. It has different states, 1 to 10, and you have a ball. And the ball is only allowed to jump downwards on the staircase. So you can only go from higher states to lower states. It's a sample space reducing process. That's maybe the simplest example that immediately tells you what that is. You can never go upwards, and how far you jump, that's a random distance. So if you're at 9, you can jump to anything between 1 and 8. Where you jump is, let's say, just a random outcome of a die with 8 faces. In comparison to this, just a normal stochastic process that's not sample space reducing is seen on the left. You have the same states again, and the ball can jump left and right with equal probability. When the ball is doing this, it's totally clear what the distribution function will be for all of these states. You see it below. The distribution function is flat. Yeah. If you look up to the sample space reducing process on the right, you see that the distribution function is not flat. What is the distribution function here? So obviously, you visit state number 1 every time you start the process. So that's the highest, and state number 2 is visited less often, etc. So that's the answer. The distribution function for sample space reducing processes is, so the lower right figure is a power law, 1 divided by I. I is the state here, 1 to 3 up to 10. And P of I is the probability to visit state number I. So this is what people call Zipf's law. It's the thing that we have already learned or that we have seen as an example in the beginning with word frequencies. If you want to know why this has to be, why this result is there, you proceed like the following. You notice that the probability to find the system in state number I is that you find the system in state J times the probability that you jump from J to I. That's a transition probability that's denoted with capital letter P, I bar J. That's read as probability that you jump to I given that you have been at J before. And then you sum over all possible states J where you could be, okay? Then the only thing that you have to do is to think how to encode a sample space reducing process in terms of this transition probability P I given J. And I don't go into the details now. I'll send you the slides, you look at them again. And what you will find at the end, after 4 or 5 lines of algebra, is that P, the probability to be in state I, is indeed I to the -1 power, Zipf's law, 1 over I. So you can prove that also in a different way, maybe also in 17,000 other different ways. That's a very general result. It's true that all sample space reducing processes lead to this Zipf's law, and they're given under certain conditions. What was the condition here? We had a process where we had this ball on the staircase, and the ball was jumping downward until it hit staircase number 1, and then we put it up to the highest staircase again. That was the driving part. Okay, the relaxing part is that it jumps downward, and once it's at the lowest state, we bring it up. It's a slowly driven process. So why slowly? Because we have to wait until it's at the lowest state and then we drive it. So for slowly driven processes, we find this probability distribution. Kind of cool. If we are not driving slowly, but if we drive the system with a probability 1 negative lambda, so at every state on the staircase where we are, with probability 1 negative lambda, we bring the ball up to the highest staircase again, then the probability of visiting state number I is I to the negative lambda. So that tells you that the probability to find states depends on 1 negative the driving rate. The power law that you find, the exact power law with exponent lambda, is related to the driving rate. By 1 negative lambda, that's the driving rate. Lambda is the exponent of the distribution function. It's also a remarkable result that you can link the driving rate of a system to the exponent of the statistics of it. And it's an exact power law. This is the proof of it. There's nothing more to it than on this page. If you have 5 minutes time, look at it. This also works for the continuous case. So if you have, no, it's not, maybe we should watch time and not talk about it, about the continuous case. If you don't believe these analytical results, you can do a little simulation. And that's what we did here and show on this plot, that if we we have such a staircase process where the ball is falling down on staircases, and we drive it with different driving rates, 1 negative lambda. So if we drive it with driving rate 0, we get the power, the Zipf's law with the power exponent of -1. That's the black line. If we drive it a little bit quicker with driving rate 0.5, then we get a blue line with much with a slope that's only 1/2. Now, you could say that it's just a very particular special case, this staircase process that I've shown you. Let's look at the right-hand side here again. We have a staircase process, but now the probability to jump to different stairs depends on the stairs. So the probabilities to jump to stair number 6 is much larger than to jump to stair number 3. So it's indicated by the size of those states. If you now let the ball jump downward, what you will find is that you still find Zipf's law. And that's now really a little bit surprising, that you're putting prior probabilities on your states, and if you're not doing it in a too crazy way, and you will still find a Zipf's law. So it's a little bit too much if I say no matter how you arrange your prior probabilities on the states, you will always end up with Zipf's law, but it's almost this strong, as I said. If you have just a normal diffusion process, now look on the left-hand side, and you have different probabilities on the states, 6 being much bigger than 1, and you jump left and right, of course, you will sample the prior probabilities if you're looking at the probability distribution of how often you visit what state. Okay? The sample space reducing process kills this completely and gives as an outcome Zipf's law. If you don't believe it, please do go through this proof. It's again not much harder than the other proofs. There's 3 dots, and these 3 dots you should be able to do if you look at the previous proof. So prior probabilities are practically irrelevant, meaning that we have a strong result. Whenever we have a sample space reducing process, we can expect, no matter how fast, depending on how fast we drive the process, we will find power loss. If we drive it slowly, it's Zipf's law. If we drive it quick, it's another exponent, where the exponent is 1 negative the driving rate. I've shown you that slide before. A driven system is a driving part and a relaxation part. Every relaxation, no matter what, is a sample space reducing process. That's an important thing. So if we're talking about driven systems or non-equilibrium systems, relaxation is always a sample space reducing process. And therefore we might have found a way to understand why there is so many power laws in complex systems, which are driven systems most of the time. And yeah, the cool thing is, with the central limit theorem for Gaussian statistics, the details of relaxing or the details of the process do not matter for the outcome of the distribution functions. That's the generality of this result. Also, if we have something like this, a staircase process, a sample space reducing process, that where you cannot reach many states, they're just forbidden, the same result holds true. It's also remarkable. So you don't have to have all transition probabilities present. That's what it means in terms of this. So let's discuss a little bit of where we find such sample space reducing processes, except throwing balls down the staircase. So we could all do these experiments, but they are maybe not the most relevant ones to throw balls down the staircases. One thing is that one thing that is interesting is to note that you can, of course, represent the staircase process as a network. So if you look on the upper right-hand side, here you have 5 states, and you're always jumping downward from higher states to lower states. From 5, you can go to all the others. From 1, you can restart the process by driving, and you're just lifting the ball up to stair 2, 3, or 4, or 5, and you do this over and over again. So you see that you have a very special network. It's fully connected on the right-hand side. It's maybe a little bit boring network, but you see that diffusion on a network of this kind would immediately give you Zipf's law or power loss. We can be a little bit more general than having a fully connected, directed network. We can look at directed acyclical graphs. These are networks that are directed and have no cycles. So let me show you a network. Let's give numbers, or let's rank the network in some way. Every node gets a number. Then we direct the network, saying we can only go from higher nodes to lower nodes. So from 5 to 1, from 2 to 1, from 3 to 2, etc. We can only go towards lower states. Now we have an acyclic directed graph. And now if we put random walkers on this graph, if we place someone on node 14, for example, then this guy will hop to another node at every time step, and within 2 or 3 hops, it will reach the lowest state, and then it stays there. So if we do diffusion on such networks, we have exactly what we had before. We have sample space reducing processes. If we do that, and if we ask how often are we visiting a given node, then we should expect the Zipf's law. And that's exactly what we find. If you look at the node visits on any type of network that we direct and keep acyclic, we find exactly Zipf's law. And no matter what the network looks like, if we take an Erdős-Rényi graph, have this diffusion there, we get this node visiting probability that follows a power law with slope -1. If we put the same thing on an exponential network, which is completely different, we get the same node visiting distribution. If we take the co-authorship network of high energy physics, direct it and make it acyclic, then we see almost exactly the same visiting distribution. There is no meaning to taking such a network. It's just to show that you can take almost any network and get the same result in the visiting distribution, which is, I think, a pretty cool result. Why is this the case? Because that's what we found out before. Prior probabilities are practically irrelevant. So that means you can not only take fully connected, directed acyclical graphs, you can take any network. You can even put weights on your network. So if you put weights from a Poisson distribution on the network and have a diffusion process on this, you get Zipf's law. If you take the weights from a power law distribution, which is completely different than a Poisson distribution of weights, you get Zipf's law. So also very, very remarkable. This is for acyclic networks. If you start putting in cycles in a network, then you will find that the slope is changing. and that's now nice. What is a cycle in a directed network? That means that from time to time you go from lower states to higher states, and it's a driving thing, and driving changes your slope in exactly the way that we computed before. Okay, so this Zipf's law, or the power law, is an immense attractor that is there. Let me now make a huge jump. I'll not discuss search processes, even though this is very nice. I'll not discuss this because we're completely running out of time. I would like to discuss this in 1 minute and then come to my final conclusion. If you have a box where there's lots of balls in it, a medium, that's the gray area here, and you have a billiard ball that falls into that box with a given kinetic energy E0, then this ball will collide with different atoms in this box, right? And it will lose kinetic energy all the time. So on the right, in figure C, what you see is, or in figure B first, you see that the initial kinetic energy E0 over time is declining. Every time it hits another ball, it gives kinetic energy to the other ball and loses its own. So this is clearly a sample space reducing process in terms of energy. And if you plot the logarithm of the probability of finding a particle, a ball with energy E, as a function of the energy, you find Zipf's law. This is known for centuries, maybe not centuries, but for at least a century. And super, super nice, I think. If you go on, no, I don't tell you this. Okay, 3 more minutes, and I'll show you something extremely nice. Consider this this staircase process again, and let's assume that with probability lambda, you go downward, and with probability 1 negative lambda, that's the driving rate, you go upward. Okay, let's make the lambda state dependent. So, for example, that at lower states you drive more frequently or less frequently, as you wish. It's state dependent now. Up to now, this lambda was just a constant. Now it's a function. This lambda as a function of x is a function, very simple function, just a derivative of the log of the probability distribution. So this allows us to relate the driving rate is 1 negative lambda, to the derivative of the log of the probability distribution. So if our statistics is characterized by P, our driving process is most likely is most likely a function where the driving rate is state dependent and is 1 negative lambda. If you want to prove this, now this is a little bit more difficult, but always follows the same idea. It also fits on 1 page. You can prove this result easily. So let me give, so on the top line, you see the same equation that we had before. If we have slow driving means lambda is a constant and lambda is equal 1. If you put lambda equal 1, what is P? Just put it in, take the integral of it, bring x to the other side and take the integral of it, and you find that the distribution function is Zipf's law, x to the -1 power. If lambda of x is another constant, is alpha, P turns out to be an exact power law. That's also what we discussed before. if lambda is a linear function, the distribution function is an exponential function. If your driving rate function lambda is a linear function, beta times x plus a constant, you get something that's called the gamma distribution. I go on with examples. If your driving rate is quadratic, you get the Gaussian distribution. If your driving rate is a stretched exponential, you get a stretched exponential as your no, I was saying stupid things. If your driving rate is a power law, you get stretched exponentials as your probability distribution. If your driving rate is a logarithm, you get log normal distribution out. Yeah, I don't go into the Gompertz, Weibull, and Salis distribution, but with very, very, very simple driving functions that completely determine a driven system, you can predict what the statistics, what the distribution function of your system is going to be. And I think I'm pretty much over time, but let me just summarize here. If you have slow driving rates in a complex system, no matter how the system looks like, just if it's a driven system, you can expect to find Zipf's law in its dynamical Zipf's law in the relevant distribution functions. If your driving is constant, you find a power law. If you have extreme driving, if you're driving the system very, very much, then you're sampling, of course, the prior distribution. And if your driving is state dependent, if you know how it's state dependent, what the lambda function is, then you understand, or you can compute, you can predict the distribution function of your complex system. Okay, I'm jumping over the thermodynamics of this, but I think now we have something. We're not quite there. That looks and smells like a central limit theorem for power laws. So whenever you have a driven system with a simple driving that's constant, you should have power laws. If your driving is a little bit more complicated, doesn't matter, you can still compute what kind of statistics you will have. Okay, I leave it with that and open to questions.
Thanks a lot, Stefan. Are there questions? Please write to the chat. I don't see anything. I can start to give, meanwhile, while people think of questions. Okay, I have a question from Guido Tiana. So what are the minimal hypotheses for a dissipative physical system to follow the SSR mechanism? Just the lack of detailed balance. So what are the hypotheses? Okay.
Yeah, I think that's it. You have to break detailed balance. You have to have a flow into the system, and as soon as you break detailed balance, you have an SSR process that's sufficiently complicated to, or sufficient to show these power law visiting distributions.
Okay, so I also have some questions because for years I've been studying this crackling noise and so on, and there are many models and so on, and also this self-organized criticality. And we always have the issue of driving and dissipation, no? In these models, there is, and typically what we find in many models is that the driving sometimes changes the exponent, as you showed here, and dissipation normally introduces a cutoff in the distribution. So I can give you some example, but I think the issue here is what is the exponent you're measuring? Because when you talk about avalanches or crackling noise, there are several exponents, several distributions of power laws. Normally these distributions are related by some sort of scaling relation. So when you say Zipf, so exponent -1, it might apply to some, but not to some other. So, and I think the key issue is, okay, which is the space that you are, how do you identify the space, the relevant shrinking space? Because you can tell you, okay, the distribution of sizes of avalanches has a certain exponent, and for the same process, if I measure something else, I get a different exponent. So,
exactly, that's a great question. And here's where the work starts. So what we tried to do is to show that self-organized critical systems like sand piles, like the Oslo model, very specific sand pile, is a sample space reducing process. So if you look from very far away, obviously this is a sample space reducing process. But if you then go closer and say, now, how do I explain the size distribution of avalanches or something? Then it becomes really, really, really hard to map this to this basic sample space reducing process. And by this mapping, you get relations that map your that map the underlying zip flaw to the exponent then that you measure, for example, in the avalanche sizes. But there's work. This is work that you have to do. That's not. It's not for free. That you then say, if you're sloppy, and that's not enough. So if you say a sand pile is of course a sample space reducing process, so therefore all the related exponents, be it energy distribution or a size distribution or waiting time distribution, should be of power law exponents -1. That's nonsense. But you have a driving underlying power law that follows Zipf's law or exact power law, but you have to map this to the quantities of interest.
Yeah. So there is another question by Florian Klimm concerning the power law for word frequencies. Are these studies that demonstrate a different power law exponent for different languages, e.g., because they have different grammar rules or different word lengths?
So if you're very tolerant, or people have claimed universality to these zip flaws in word frequencies. If you look closer, that's of course not the case, and you can even find variation. So first of all, you find a double power law in zip flaw if your corpus gets strong enough. It's -1 for the first 10,000 most frequent words, and then it shows a power law of -2 for the super unfrequent words. It has been claimed that there's universality to this -1, which, if you look closer, is not the case. Even authors vary in the exponents. If you can safely measure those exponents, it's another issue. What I did not talk about is the restarting process when you do sentences. Usually when you come to the end of a sentence, you make a dot and then you restart. But it's not a completely independent restart with the same kind of vocabulary, of course. And what we found is that different ways of composing sentences and linking sentences can be specific to authors, and this indeed changes a little bit the exponents, which we attribute to different driving rates or restarting rates. Yeah, we have a paper coming out in the next couple of days. It's not a very shiny journal, but will be out in +1 in the next couple of days or weeks, where we exactly focus on this. How long does how complicated does a grammar have to be to show realistic statistics in sentence formation?
Nice. So there is another question by Elia Mascolo. Could you repeat what you called extreme driving, if I remember correctly, and what you said expected distribution?
Extreme driving is if in the most extreme case is that we are doing what? Is that after every step, we're not waiting for the system to relax. We're driving it at every step, and then we are just sampling the prior distributions, the prior probabilities. So here on the left-hand side, yeah, when we can go back and forth and drive the system at every state, at every position. So if it's at 5, if we can bring it to higher states at every point in time, then we are just sampling the prior probabilities. Yeah. Okay. I see where I'm failing now. It's why should you, with the way I've used driving, sample lower states. So so extreme driving here means you drive pretty frequently, not at every state, but very often, so that you also can relax. You have some time to relax to lower states.
So there is also a question by, so I think Elia Mascolo is satisfied by the answer, so he wrote. And Tony Giorgino asked, in the lambda versus p results, okay, it's shown as a
what lambda
versus p.
Okay, yeah.
Okay? It's shown as a function of one x-axis, but I presume it holds in arbitrarily higher dimensions as long as you find a suitable ranking projection x subject to forcing.
Yes, we played around in 2 dimensions and nothing special there. Right, good question.
Dimensional, yeah. So maybe I could mention an example that you may look at. There is a famous model of the Barkhausen noise that is essentially a mean field model. And there you have an exponent that depends on the driving rate, linear dependence on the driving rate. The question is whether it's possible, but the exponent is not 1, so in the limit of 0 driving.
Okay.
And so maybe you could have a look at that and see whether you can mark.
That's great.
In the thing. And it turns out that there was another paper that showed, this is a mean field model. There was a paper that also showed that, I will send you some of this literature, that also showed that only in mean field you get this linear dependence of the exponent from the driving rate, otherwise you don't. The exponent doesn't really depend on the driving rate. And now here also your model seems quite mean fieldish, no? As so do you think space dimension can have a relevance in these scaling relations? So the fact that, I mean, here you say you drive the state, you go from one state, looks very mean field, no? If you think of phase transition, is like you have a free energy and you jump from free energies, is a mean field picture of a phase transition. Have you thought about mean field versus non-mean field?
Yeah, maybe, yeah, we never called it mean field, but if you, for example, embed your states in a space or something, this brings about all the problems that I mentioned before, that you have to map a real system back to this idealized version where you have these different states just adjacent to each other, and where you just go from higher to lower ones. As soon as if you have to embed into real space or other settings where you have additional constraints, then then you might get quite different exponents that are explainable through the mapping. So somehow I would agree to call this mean fieldish. In that sense, that every geometrical details or something is completely taken out of this, and that just the order of states matters, or just the detailed balance is broken. Yeah.
Okay.
That sense, yes.
Yeah. Very good. So I think there are no other questions for Stefan. So I would thank him a lot. I can applaud, but unfortunately, that's the missing thing from the online. And anyway, thanks a lot. So, yeah, somebody showed how to do it. Nice, nice emotion.
Thank you.
Okay. So here is the, okay.
Thank you all for listening.
Thanks.
And now hope to see you soon.
I can introduce the second speaker of today, who is Florian Klimm. So Florian received a PhD in biomathematics from the University of Oxford, and then worked research there afterwards as a doctoral prize scholar. Currently, he's a research associate at Imperial College London and at the University of Cambridge. His research interests are the analysis of biological systems and single-cell sequencing data with tools from network science and topological data analysis. And today, will tell us about protein interaction data. So I leave the floor to Florian.
Yeah, thank you very much for the organizers, and also Stefan for this great talk. I have to confess I only have one power law in my whole talk. But yeah, otherwise I will talk a lot about networks and different ways to analyze them. I'm going to talk about hypergraphs and node-weighted networks. And as I said, the biological focus will be protein interaction data. This work I did when I was in Oxford. Yeah. So the main focus of my talk is going to be proteins. Proteins are active molecules in the human body which fulfill many different biological functions. So one thing maybe most of you know are enzymes, which are, for example, splitting up metabolites to then the body further use those split up metabolites. Something else known is hormones, which are messenger molecules. So hormones are produced by one part of the body, and then they go to another part of the body and basically tell the body to change some function, and it does it by interacting with receptor. And something that recently got a lot of attention are so-called antibodies, which are really important for the immune response. You might have heard about them because the American president on the weekend got like some medication which consists of artificial antibodies. So you see that proteins have many different biological functions. One important thing to consider is that they usually don't fulfill their function by themselves, but actually by interacting with other proteins. So for example, you have metabolic pathways where a protein is interacting with a metabolite, and then another protein is interacting with this metabolite again. And so important, for example, is the citric acid cycle. But there are many different metabolic pathways which fulfill many different biological functions, and they are also all interacting with each other. And so this interaction between proteins we can measure with different biological experiments. And so usually it looks like that we really have like one protein to another protein, and they bind to each other with some kind of electrostatic interaction. And so they're really docked to each other. And so this pairwise interaction we can then represent in graphs. So for example, here now we have a node representing one protein and another node representing the other protein. And if there's an interaction between those two proteins, we create an edge. And so we can repeat this for all proteins in an organism. So for example, in a human body, we have about 20,000 different proteins. And then if we combine all this data together, we get a network. So that's roughly like how a protein interaction network looks like. So this is a small example. As I said, in the human case, it would be much larger with about 20,000 proteins. And so there are two, I would say, central paradigms which I want to talk today about, which are important when you consider such protein interaction networks. So the first is that we can assess the centrality of proteins in these interaction networks. And proteins that are more central than others tend to be more essential. And essential, we mean by this, if we knock out a certain protein, so we don't allow an organism to produce this protein, then the body or the cell is not able to survive without this protein. Whereas for other proteins, it is perfectly able to survive. It might just have some problems to adapting to some certain environments, but overall it is able to survive. So that's the essentiality, centrality relationship. And the second thing is that proteins tend to interact with other proteins which have a similar biological function. And this creates some kind of modular structure. And so what I mean by this is that there are parts of the protein interaction network where all the proteins there together fulfill a certain biological function. And I want to use like one metaphor that you can think of this protein interaction network a bit as like a social network for a cell. So if, for example, if you would now think about this network not as a protein interaction network, but rather as a social network, for example, for a university, you would have that all the people in one department are acting a lot with each other. But then, for example, the heads of the department meets with other heads of the department to discuss like the bigger research agenda of the university, and those would be then the central essential proteins. So that's kind of like the metaphor you can have in mind. And what I'm going to talk today about is two things, how we can represent or analyze those two occurrences. And so one thing is I'm going to talk about is how hypergraphs can help understand this relationship between centrality and essentiality. And then secondly, I'm gonna talk about how we can use node-weighted networks to allow us to detect such modules in different cell types. Okay, yeah, so the first part of the talk about the hypergraphs, there's a manuscript of bioRxiv. It is with joint work with Charlotte Dean and Gesine Reinhardt, who were my supervisors at Oxford. And you can find the Python code on GitHub and also the data. So I said earlier that there are pairwise interactions between proteins. However, there are also something called higher order interactions. So those are interactions between proteins which are not pairwise, but you basically need not only two proteins to come together to form an interaction, but you need more than two proteins to come together to form this interaction. So for example, there's something called the PIM complex, which consists of three proteins, PIM, Y14, and the MAGO. And then there's also something called an exon junction complex, which actually consists of four different proteins. And so we can represent such higher order interaction in something called a hypergraph. A hypergraph is a generalization of a graph. So a graph consists of nodes and pairwise interactions, and a hypergraph consists of nodes and hyperedges, and the hyperedges can connect more than just two proteins. So for example, this exon junction complex we represent as a 4-edge, and this PIM complex we can represent as a 3-edge. So on this hypergraph, we then have these hyperedges, we can have very different cardinalities. Some of them will have like just a small cardinality of 2, whereas others will have a large cardinality of maybe consisting of up to like 30 different proteins. when we analyze such a hypergraph, we can compute different metrics describing this hypergraphs. One simple thing is to look at the degree of a node. So you might know that in a graph, the degree of a node is just the number of edges connecting to it. And so now similarly in a hypergraph, the hypergraph degree of a node is the number of hyperedges connecting to it. So for example, here node D has only one edge connected to it. So that's why it has a degree 1. And for example, node 2 is connected to 2 hyperedges, one of cardinality 2, one of cardinality 3, and that's why it has a degree 2. Yeah, and so this is one measure of centrality, the degree of a node in the hypergraph. We take data from the Reactome database to construct a hypergraph of protein complexes in Homo sapiens. We have 8,000 different nodes representing proteins, and we have about 7,000 hyperedges representing the protein complexes, which connect those proteins. And you already know that, as I said earlier, there are about 20,000 human proteins, and here in this network we have only 8,000. So it means not all human proteins form those stable complexes, but a considerable chunk of them, so approximately half of them. This is a just visualization of the hypergraph we obtain, and the color indicates the degree, from red being larger degrees and blue being smaller degrees. And what you already can see is that what I said earlier, that we have some proteins which are more central than others. So for example, here now those central have a high degree and are very central, whereas those have a lower degree and are more on the periphery and have actually some kind of, but they are nevertheless clusters together, so you would assume they maybe have some kind of functional similarity. So the first thing we wanted to check is whether the hypergraph we obtain, so this graph, whether it is similar to a random graph that we would create. And so we explore here 2 random null models. The one is developed by Phil Chodrow. It's a configuration model where we have the same number of hyper edges as the original graph. So for example, here in the original graph, we have 2 edges of cardinality 2 and 1 edge of cardinality 3. And we have the same in the configuration model. And also in the configuration model, you have the same degree for each node. So here observe this node A, for example, had a degree 1 and C had degree 2, and the same for this network. However, the cardinality of the edges connecting to the different nodes can be changed. And then we also develop something which we call the R-type null model, because it's somewhat similar to an Erdős-Rényi null model, where we fix only the degree, we fix only the number of hyperedges of each cardinality, but we don't fix the degree. So that's why the degree of the nodes can be changed. And what we find is that, without going into too much detail, that the structure we obtain is, for these 2 null models, is very different than from what we observe in our actual data. So for example, if we look at the number of connected components that our graph has 253 connected components, whereas if you do this null model calculations, you have very small number of connected components. So you have 1 for the configuration model, and we do 100 realizations. So for the R-type null model, we see a bit of a distribution, but it's on average something like 2 or 3 connected components. So this means what we observe is not what we would observe at random if we fix the cardinality of the hyperedges. So one thing to take in mind when analyzing hypergraph is that we can always take a hypergraph and we can create a graph from this. So it's something called a representing graph, where we have the same set of nodes, but we replace each hyperedge by a clique of pairwise edges. So for example, a 3-edge A, B, C would be replaced by 3 edges A, B, B, C, and A, C, as seen in this illustration. And now, of course, we can ask, well, do we get different answers when analyzing the representing graph than to the hypergraph, because mathematically this is a much easier object. And also there has been so much literature developed of how to analyze a pairwise graph. Why should we bother analyzing this more complicated hypergraph? And so if we look at the degree of the nodes, we find first of all that the degree if in the graph seems to be broader, the distribution, than in the hypergraph. And this occurs because exactly we replace those hyper edges by pairwise edges. So for example, here this node C would have a hypergraph degree of 2 because it has 2 hyper edges. However, in the representing graph, it would have a representing graph degree of 3. So basically the degree in the pairwise graph is larger. So that's why the degree distribution is going to be broader for the representing graph. And when we look at the correlation between graph degree and hypergraph degree, we find a moderate correlation. So I think the Spearman correlation is about like 0.3 or something like this. And we find that the highest proteins with the highest degree are the same in both cases, but there are some proteins which have basically the degrees flipped. So they have a high representing graph degree, but not a very high hypergraph degree, and vice versa. So now we can ask, well, which of those representation is more fruitful? And so what we looked at is which of those centrality measures, hypergraph degree or representing graph degree, is in better agreement with this gene essentiality information. And so we look at the mean degree for essential proteins, conditional proteins, or non-essential proteins. So I said earlier, essential proteins are proteins which are a cell needs to survive, whereas non-essential proteins are proteins which a cell doesn't need to survive, and conditional are basically proteins which are necessary and under certain conditions. So for example, if there's increased temperature, then the cell needs it, whereas if there's a normal condition, then it doesn't need this. And what we find nicely is that for the hypergraph degree, is that the essential proteins have the highest degree, the conditional have the medium degree, and the non-essential have the lowest degree. So that seems to indicate that really there is this representation or this correlation between essentiality and hypergraph degree, whereas for the representing graph, we don't find a clear relationship. So we find that the essential proteins have a higher mean degree than conditional proteins, but actually non-essential have a higher degree than the essential. So this is some indication that the hypergraph representation might be more fruitful than the representing graph representation. So this is now the one power law I will talk about. So something which has been reported for networks is if there's a power law relationship between the local clustering coefficient and the graph degree. So if there's this power law relationship, that this is a sign of some kind of hierarchical organization. And so if you look at the representing graph, we find that there's a power law. So it's not very strong, but it is statistically significant, the correlation between hypergraph degree and clustering coefficient. However, if you look at the hypergraph variant of the local clustering and the hypergraph degree, we don't find a statistically significant correlation between those two entities. And so this seems to indicate that we might observe this hierarchical organization just from the projection from the hypergraph to the representing graph, and not actually in the biological system itself. And so we actually think this might even have implications for other type of data where we have some kind of information which is actually non-pairwise. So for example, you could think of like co-authorship networks. So you have co-authors and they write a paper together, and then this paper would be a hypergraph, it's a hyperedge between the authors. And then when we look at the co-authorship network, which is then basically the representing graph of this original hypergraph, we might observe such a hierarchical organization. However, in the original hypergraph, we don't observe this. So I think there's still some room for exploration if other people are interested to explore whether this is a more general phenomenon and not only restricted to our data set. So to conclude, my first part is proteins interact in higher order interactions that can be represented as hypergraphs, a generalization of graphs which allow this higher order interactions. When we look at the human protein complex hypergraph, we find that it has structure which is quite different from two random null models. We find that essentiality is in better agreement with the hypergraph degree than with the graph degree. And lastly, if we do this projection of the hypergraph into a graph, we might find this mirage of a hierarchical organization, which is not there in the original data. Okay, now let's come to the second part of my talk, where I'm going to talk about how we can use node-weighted network and single-cell RNA sequencing data to look at protein-protein interaction networks and detect some kind of functional modular organization. So this manuscript is on bioRxiv. The code is also on GitHub and will appear in BMC Genomics. And this is also in collaboration with Charladine and Gesine Reinhardt, and also with our collaborators from Novo Nordisk, who are a pharmaceutical company looking especially at liver diseases. So the human body consists of approximately many trillions of cells, which belong to hundreds of different cell types. And those different cell types come in many different shapes. So for example, you have nervous cells, which are very thin but very long. We have blood cells, which can be very small and round. And the largest cell is the oocyte, and the smallest cell is spermatoid cells. And all the cells fulfill very different biological functions. However, something important to keep in mind is all of them, first of all, originate from the same cells, which are stem cells, which can basically differentiate in all those different cells. And also all the cells have actually the same genetic material. So they have the same blueprint of how to produce proteins to fulfill their biological function. But then for whatever reason, they look very different and do very different things. And so the central paradigm of transcriptional biology is basically that you have this genome where you have parts of the genome, so of the DNA, which can be transcribed into mRNA, which is then translated into proteins. And those proteins, some of them also regulate this transcription. So this is something called transcription factors, who, for example, then change how different the parts of the genome are transcribed into mRNA. And we're going to look today at this transcriptome, so which is this in-between stage between genome and proteome, and we're going to analyze this to find how the different cells use the genome in different ways to fulfill their biological function. So as I said earlier, also protein interactions are important for proteins to fulfill their different biological functions. So it very much is reasonable that actually also the protein-protein interaction networks are different for the different cells or different cell types to fulfill their biological function. And how do they fulfill their different biological function? They do this by having different gene expression in different situations. So for example, we know that healthy and diseased cell states have different protein interactions because they have different gene expressions. And also we know that the protein interactions are different with different cell states. So just to give you one comment about the healthy versus disease state. So for example, you might always read in some kind of paper that people say, well, there's a certain gene which is associated with cancer. And so what they mean by this is that if we look at cancer cells, we're going to find that a certain gene is overexpressed in a cancer cell versus a healthy cell. And we find similar things also in other diseases. And so now we're going to talk quickly about single-cell mRNA sequencing. So single-cell mRNA sequencing allows us to identify which genes are expressed in different single cells. And so what we're going to test now is that if we look at the protein interaction network, that there are indeed those functional modules that I talked about earlier. So this is the different part of the protein interaction network fulfilling different biological functions. And we're going to find that different cell types have different parts of the protein interaction network active. And so really different cell types fulfill their biological functions by having different parts of the protein interaction network being active. So what is single-cell mRNA sequencing? So first of all, maybe we should talk what is new about single-cell mRNA sequencing, because until recently, people did only something called bulk mRNA sequencing. So basically, they take a tissue sample. So this can be, for example, a skin sample, and then they take all those different cells which are on the skin cell, and they basically create more or less like a smoothie out of this. And then they can measure the average gene expression from all of those cells which are in one of those tissue samples. However, recently now, in the last decade, there has been developed experimental techniques where you take those tissue and you basically can separate the different cells out, and then you can measure the gene expression for each of the different cells. And so this gives you then some interpretation of like all the different cell types that are present in one tissue sample. And you can look at the gene expression for each of the cell types in one tissue sample separately. And there are also now recent developments where researchers develop so-called the human cell atlas, where they produce this for all cells in the human body. But this is a huge experimental effort. To give you some idea about the booming of these techniques, so about 10 years ago, the first of those single-cell high-throughput sequencing techniques have been developed, where I think people looked at 8 cells at one point in time, and now people look at about 100,000 of cells in one experimental study. And there are now experimental techniques available or that are commercialized, so for example, 10x Genomics, where you can do this with some experimental effort and some money in a lot of different lab settings. The data we will have in the end, after a lot of pre-processing and cleaning, will be in the form of a matrix, which is the size number of cells times number of proteins. And each entry gives you basically a strength of the protein presence in a certain cell. So what do people do when they analyze the single-cell mRNA sequencing? So what they do is some kind of dimensional reduction. So this is UMAP, which is a topological dimensional reduction tool, but you can think of it as something like a PCA. So now each of those dots is one cell, and they are in this high dimensional gene expression space of like 20,000 proteins. And we can create this dimensional reduction, and we find that cells are closer to each other if they have a similar gene expression than and they're further apart if they have the quite different gene expression. And we find those clusters, and those clusters of genes represent genes of the same cell type. And then, so in this case, for example, you find 3 different cell types. However, you can also imagine that they are now something like sub-cell types. So for example, this is one cell type. However, then there's also, if you do a hierarchical clustering, you might find that this is falling apart into 2 clusters. And we also now can look at the gene expression of those different cells and different cell types. So for example, this is now colored, the gene expression of 3 different genes. And you find, for example, that this gene is highly expressed for all cells in this cluster, whereas this gene is highly expressed in this small cluster, but not in the other genes. And so those kind of genes which are highly expressed in a certain cluster are called marker genes for a certain cell type. How can we detect marker genes? There are many different biological tools out there, but what people essentially do is they look at all cells in one cluster and all cells not in the cluster. So you basically have 2 groups, and then you can look at the expression of the gene, and you find kind of like 2 distributions, and then you do some kind of statistical test whether those 2 distributions are similar or not similar. So in this case, the distributions are very similar, whereas here they're quite different. So you see that for cells in a certain cluster, the gene expression is underexpressed. And so if you do, for example, rank sum test or a t-test, you're going to find a very small p-value for this case, but a fairly high p-value for this case. So this is not differentially expressed or not statistically significant differentially expressed, where this is statistically differentially expressed. And so we can repeat this now for each gene and for each cluster. So basically, we then have for each cluster a list of 20,000 p-values, which tell us whether each gene is differentially expressed, yes or no, or how strongly it is differentially expressed, if you look at the p-value. And now the question is, how can we integrate this, or how can this help us to see what I said earlier, how the different cells utilize the protein interaction network in different ways. And so to recapitulate a bit, we take the single cell expression profile. So this is the matrix with cells times proteins. We do this differentially, we do this dimensional reduction, this clustering where you find different cell types. We get this p-value of differential expression for each gene and for each cell type. And now we're going to integrate this with protein interaction network to create something called node-weighted protein interaction network. And then we're going to find a maximum weight connected subgraph to find this active module, so the part of the protein interaction network which is most active. So what do we mean with finding a maximum weight connected subgraph? So assume we have assigned to each node in our protein interaction network a score, where a positive score is it is a marker gene, whereas a negative score that is not a marker gene. And so now we have something called a node-weighted network. So we have this network and we have weights on the nodes, not on the edges, which is the more general, the more widely discussed structure. So we talk about node-weighted networks here. And now we want to find a maximum weight connected subgraph. And so giving a vertex-weighted graph, with a graph with vertices, edges, and weights on the vertices, we want to find a connected subgraph which that maximizes the score, which is the sum over all weights of this connected subgraph. So, for example, we could just take a look at a single node. So this single node has a score of 5. We could now connect it to the neighbor. Then those subgraphs, all those two together, has a score of 7. We can connect to the next neighbor, which has a negative score. So then the score is +5. And now we can connect to those two neighbors, and we have a score of in total 9. And so in this case, it's actually the maximum weight connective subgraph. So this is from all the possible subgraphs we could construct from this graph, the one with the highest score. And one thing to take in mind is that this maximum weight connected subgraph might consist of nodes with a negative score. So how can we find such a active, or there's such a maximum weight connected subgraph? What we actually do is solve a slightly similar mathematical problem, which is called a price collecting Steinerty problem. And there are fast algorithms out there which are heuristics, because it's an NP-hard problem. So you need heuristics to solve it. And however, the nice thing is that this algorithm actually solves it to optimality. And for our 20,000 node protein interaction network, it takes about 10 seconds because it's quite fast. So that's quite nice. So now we apply it to one example. So as I said earlier, our collaborators were specifically interested in liver network or liver tissues. So we created a liver single cell sequencing data set, and we did a clustering where we find the different cell types, and we, for example, also find different sub-cell types in the hepatocytes. And then, to give you one example, for one of the hepatocyte clusters, we find this long list of proteins with their differentially expressed gene p-value. And we have this long list, and usually what biologists now would do is they would look through the long list and would look whether they find certain biological functions with like certain proteins which are strongly differentially expressed. However, if you use our functional module detection pipeline with this maximum weight connected subgraph, what we find is that we we find proteins which are strongly differentially expressed. So for example, this PPP1R3C, which is actually most differentially expressed, or also SEP1, which is the second most differentially expressed. But these proteins are connected to each other via other proteins, which are actually not strongly differentially expressed. So for example, this EGFR and this APP. So if you look at this list of differentially expressed genes, they're like rank 373 and 1,800, and our differentially expressed gene analysis. So you would never say that they are strongly differentially expressed. So especially this EGFR one. However, when we use our functional model detection tool, we find that they have an important connector function by connecting different proteins which are strongly differentially expressed. And actually, if we then look at those genes or these proteins, what we find is that both of them are actually membrane proteins. So those are proteins stuck to a membrane, which are known to interact with many different other proteins. And especially the EGFR is epidermal growth factor receptor. So it's a receptor which is embedded into a membrane and there to interact with other proteins, especially with this epidermal growth factor. And this growth factor is known to alter the gene expression of other proteins. So this really gives us some indication that the proteins we pick up here really have some important biological connector function. So now we can apply this to these different clusters we obtain. And for these different clusters, we really get different structure modules. So we find different parts of the protein interaction network to be functional active. And also then we can look at something called GO-term enrichment. So GO-term enrichment is basically asking for a certain set of proteins, are we aware that they have a certain joint biological function? And we find that those different functional modules have different structure modules, they have different biological functions. And so, for example, one of them is a response to stress, which might indicate that there's some kind of inflammation going on. And also others, for example, cluster H4 has, for example, this alcohol metabolic process, which is also known to be very important to the liver. So this gives us now indication that those different structure modules for the different cell types or different cell states actually give us different functional modules. So there's an online tool available if you should have some data set you want to analyze. But as I said, there's also all the code on GitHub, which you can look at. So to conclude, in the analysis of single-cell RNA sequencing data, we are often challenged with a long list of genes and associated p-values. We can integrate this data with protein interaction networks to obtain different active modules for different cell states. And for liver data sets, the detected functional modules structural modules are indeed functionally relevant and reveal potential drugs targets. Because what I haven't said earlier, so now those connector functions of those proteins might be very good drug targets, because what drugs usually do is to interact with other proteins to basically alter their ability to interact with other proteins. So we might actually, in a certain inflammation pathway, for example, we might interact with those proteins to block their function. Okay, yeah, thank you for your attention, and thank you for the organizers who invite me to speak. As I said, all the code is on GitHub, and manuscripts for both projects are accepted for journals, but also are available on bioRxiv. And I'm looking forward to your questions. Thank you.
Thank you, Florian. So I'm looking for questions. Maybe I can start to ask some questions while people think about it. So you have this protein interaction network, but I think the one key issue is how good is your protein interaction network, because many predictions will depend on how well have you been able to assemble your network. No? And for instance, there are a lot of there is a lot of information in the literature, like on pathways. So is this pathway information introduced into your protein interaction network? So if you go, for instance, to KEGG, you have a lot of relations between genes and so on, and these are believed to be describing how genes are regulated. So are these, for instance, KEK pathways are present in your interaction networks,
yeah. So yeah, good question. So there are different ways to construct a protein interaction network. What we have done in the second study is to use BioGrid, which is an aggregation database of published high quality interactions which have been found in different publications. So for example, a certain publication might find there's an interaction between protein A and B, and then this is gonna be in this database. So this has the advantage that the interactions have a high or have a low false positive, but they might have a false negative. So just because two interactions have not been found in a certain study doesn't mean that it's not present. There are different approaches in so-called high throughput studies where people basically study experimentally all those possible pairwise interactions. This is usually a higher false positive, but a lower false negative. And it doesn't have the problem of, for example, literature bias. So literature bias is, for example, when people or biologists find a certain protein very interesting, then they are studying extensively the interactions of a certain protein, and then you might find way more interactions for this certain very interesting protein and less for other proteins which are not as interesting. So we have not specifically introduced the KEK pathway. But KEK pathway would be present in these GO terms. So we would actually just basically check whether a certain biological pathway is enriched in the functional modules we find in the end.
And then you classify an interaction, a physical interaction between two proteins, or just the fact that one gene relates to another. Like if you have a transcription factor, no? I wouldn't say the transcription factor is necessarily interacting with the protein of the gene that is transcribing, no?
Yeah, that's a good, that's again, very good question. So the BioGrid has an aggregation of actual physical interactions and genetic interactions. So for example, transcription factor interaction. And so we incorporate both information. Yeah, but you could restrict yourself, for example, only to physical interactions or only genetic interactions.
So there is a question by Francesc von Kloss. He says, technical question, which clustering algorithms did you use in the UMAP projected data? Also, do you see differences if you use T and SNE or other embeddings? So is there a difference depending on the...
So first of all, let's talk about TSNE, UMAP. We tend to see not a strong difference. I have to say UMAP tends to produce nicer figures. That's why we recently used more UMAP, and it also seems to be more in fashion in the community than TSNE. However, both of them are fairly appropriate. We used for the clustering a Louvain algorithm clustering. So basically what you do is you have all this, so you have all the cells in this UMAP, and then you create a nearest neighbor graph. So you connect all your cells to, for example, the 6 closest cells in this gene expression space. And then you have now a graph, and you can cluster now those with different graph clustering algorithms. And we use modularity maximization algorithm, which is based on a Louvain maximization.
Okay, thank you. Other questions from somebody else? I think we see no other question. So I think we can try to thank the speaker again with a nice clapping of hands. Let's see if I can find it. And that's cannot find it, but okay. So we thank Florian again, and also Stefan, who spoke before, and Thank you everybody for participating. And as I said, 20 of October, 20 of October we'll have the next seminars with Michael Small and Filipa Valdeira. And I hope to see you there next time. Okay, and you will find everything recorded on the YouTube channel of the Center for Complexity and Biosystems. You can find this on the webpage of the seminars. You can find the link. Okay, thanks a lot, everybody. Thank you.
Thanks again, Stefano.
Thanks.